Welcome to the Case Western Reserve session. This is a session going to focus on mechanical and aerospace engineering, joined by our professor who is going to take over, but a few logistical items if you've not been to these sessions before. There is a Q&A box, so please feel free to add your questions to that box. We will have time to address all of your questions. The other thing you'll note is we do have a transcription going. So for anyone who maybe has a weak signal, hopefully you can be able to read a little bit of that transcription for you. Otherwise, my name is Leanna Carroll. I am one of the admission counselors in undergraduate admission. I'm so glad to be joined by our awesome faculty, who I also hear has a great story and background just with Case Western Reserve in general. So I'll let you take it away and introduce yourself, and I'll go into the background.
Well, thank you. My name is Paul Barnhart. I'm a professor of mechanical engineering, and I have a little presentation I'd like to show. It's a PowerPoint slide. Let me bring that up. I got to share my screen first. There we go. All right. All right. This is mechanical aerospace engineering at Case Western Reserve University. I've also included the link to our department website, but if you just simply Google CWRU space EMAE, it'll take you right there. You don't have to memorize this particular web link. My email address here, jb4@case.edu. I've given you that in case you want to reach me sometime after this presentation. If you would have questions, I'd be happy to answer them. I'm going to go through a bit of a description of what happens in our department, what experiences our students typically have. But I do want to mention that I am a former graduate of this very department. I earned my bachelor's in mechanical engineering back in 1983. I stayed on as a graduate student and finished my master's of fluid thermal and aerospace sciences, what we now call aerospace engineering, in 1985. And I eventually came back after working to pick up a PhD on a part-time basis in 1995. So I've been within this department for quite a while. While I was a doctoral candidate, I was also asked to teach classes since we were short of faculty. So I've been teaching since the 1990s. I've worked other places and was not involved in the department for some time, but when I returned to the Cleveland area, I started teaching again as an adjunct. And then about 10 years ago, I made a switch from working in industry to becoming a full-time professor. So I've seen this department from different angles for many decades. I'm going to try to give you my best impression of what it's like to be a student here at Case Western Reserve in our department. So I'm going to talk about some typical student groups. There's a picture on the first slide. This is a DARPA Urban Challenge team, which had designed a autonomous vehicle, a car that could maneuver on streets and avoid obstacles and be able to understand when to stop and go. And that was tested in a pretty safe environment. That was quite an accomplishment in terms of robotics and controls. Other things our students get involved with are things like high power and high altitude rocketry in these two pictures. And we'll talk more about this in the next slides. But the department's mission, I think, is terribly important. Our mission is to educate and prepare students for leadership roles in the fields of mechanical engineering and aerospace engineering, and to conduct research for the benefit of society. A second bullet point I want to emphasize is I really do believe this is the most important thing we have to offer. We emphasize fundamental engineering science, analysis, and experiments to ensure our graduates will be strong contributors in their work environment, be prepared for advanced study at top graduate schools, and be proficient lifelong learners. So our emphasis on the fundamentals is truly important. I've lived through it personally. I attest to its strength. If you understand the fundamentals of the topics we teach, you'll retain that for the rest of your life. As your career progresses and technology changes, you won't lose the fundamentals. You can apply them in new areas. You'll be very, very proficient, and you become lifelong learners. It's a great way to teach a complex field like mechanical or aerospace engineering. I went through it myself, and I teach it back to my students again. It's the way to do it properly. If I had to summarize what we do in this department, we design and manufacture things that move through time and space, and I'll talk more about that in a moment. This is a snapshot of our department. We are an ABET accredited undergraduate Bachelor's of Science degree in 2 programs. The first, aerospace engineering, the second, mechanical engineering. We have a streamlined mechanical and aerospace double major where you can get 2 majors and a single bachelor's degree, and you can earn that in 4 years. And the only cost to get it done in 4 years is to take 1 additional class, which is, I think, quite a bargain. But I'll talk more about that double major. It's quite attractive to our students and how we actually make that possible for you if you were to choose to do it. We also have an integrated Bachelor's of Science, Master's of Science program where you can combine and overlap some classes and complete in 5 years both your bachelor's degree and your master's degree in the field of study. It's possible, and some students do, earn a double major in both mechanical and aerospace for a bachelor's degree, and then continue on in either mechanical or aerospace and earn a master's degree in 1 more year of study. We can actually make that happen for you. Our undergraduate enrollment is about 350 students, but I want to be a little careful about that. In the case School of Engineering, you apply to the School of Engineering, not to a department. And so typically students are undeclared for their first year, their freshman year, and then by the end of their freshman year, and certainly by the start of their sophomore or second year, they become enrolled. So our snapshot of 350 enrolled students doesn't really count the majority of the first year students, though they will eventually join our department. So the student enrollment is, I'd say, a little bit larger than 350, probably add on about another 100 students in total. We graduate about 100 students per year. It seems to be slowly increasing with total number of students year by year. Of that roughly 100, about 70 will pursue just the mechanical engineering degree. About 5, and sometimes less than 5, will only major in aerospace engineering alone. But a larger numbers, 25, and I see numbers as high as 30 some years, will do the double major in both mechanical and aerospace engineering. So that's quite attractive for an option for your majors in our department. Doing both majors requires a little more effort, a little more diligence, but certainly doable. And I think the benefits are certainly worth the effort. And we'll talk about that double major as I go through this presentation in more detail. Roughly 25 to 30% of our students will do a co-op, and that's kind of a broad number. It will change depending upon circumstances. You typically take a semester off, or it can be a semester in the summer or a summer in a semester. Sometimes you do 2 co-ops as opposed to just 1. But in the time you're away from the university, you can earn $20,000 in salary, roughly, depending upon your employer. And people find that beneficial for a number of reasons. Some students just want to take a break from their studies. Others want to see what it's like to work in a particular company they may be interested in eventually working for in the future. And if that's your interest, if you start out as a co-op, often the companies will give you an offer for employment upon your graduation, so it sort of streamlines your entry into a business or an employer of an interest. And students take advantage of that. In up and down economies, our graduates find jobs. Now, that is actually a very true statement. I have not seen any students over more than 10 years who have struggled to find employment more than 6 months after graduation. Most have job offers before they graduate. A few will find offers in a few months afterwards, and some aren't even looking because they want to graduate, take a little time off in the summer, and then look for work. I don't have students coming back on any regular basis saying they can't find work. That never happens. And the few who are struggling, I can usually give them some quick pointers in terms of how to interview better, and they all have found very, very challenging and rewarding work. So I really want to stand by that statement. So our graduates find jobs, absolutely. And one of the reasons is mechanical engineering is a really important discipline and skill, and there's no end of things mechanical engineers get involved with, and their skills are always required to build and maintain the world. It's a very fundamental discipline, very much in demand. In terms of our faculty, I'll give you a quick snapshot of who we are. We have about 18 members of the faculty. We're trying to hire a few more right now, so that number will probably increase next year. Of those, 4 are female faculty members. We have had a member of the National Academy of Engineering on our faculty. He's now emeritus. We have 1 member of the American Academy of Arts and Sciences, which is kind of unique for a mechanical engineering faculty to have that kind of diversity. We have more than 20 research associates, research faculty, postdoctoral fellows, adjunct faculty, instructors, and secondary faculty who support the primary full-time faculty in their mission. And that number of more than 20 kind of fluctuates based upon primarily how much research we need additional support to accomplish. We have 7 professor emeriti. What that means is they are retired, but they still have an office and a presence in our department. They no longer teach on a full-time basis. They may still be involved in some modest research. Perhaps they're trying to get a student or 2 through their PhD studies. And we encourage them to participate in the department as they see fit. And our emeriti professors are very talented, very brilliant men, and I tend to use them still when I have to have a thesis defense committee. They're really good people to have involved in reviewing research work. Very much appreciated. And these professors are my former professors. The last one that was one of my professors finally retired a year ago. It's kind of sad to see them all go, but we're getting older year by year, every one of us. Now, there are some distinctive educational facilities we have. They're located in a place called ThinkBox. It's a building relatively close to our offices here on campus, a very short walk. And we've kind of co-located a bunch of other assets and equipment into one location for students to use. Now, we used to have a shop in a building just across the quad from ours where you could learn how to do metalworking, operating a metal lathe, milling machines, basic fabrication, welding, the things you would do to build things out of metal, because as mechanical engineering, as a discipline, everything we do principally is working with high-strength alloy steels and such. There's a full wood shop that's available for your use, and once you've been through a course, it's typically the first course you take in our department, we'll have you actually work with this equipment so that you are trained, and then for the remainder of your years, you can go back to these facilities and use them over and over for anything of interest to you for a student project, for your senior project. I'll talk about that. That's quite important. Or if you're involved in doing club work, you have access to these facilities. If it's your own personal hobby, you can still use the facilities. So it's quite an accomplishment to have that at your fingertips. There are more advanced equipment in what we call the Reinberg Product and Process Development Laboratory. There are rapid prototyping machines. Those are things like 3D printers. We have laser cutters. We have some of the most finest and more recent machining capability that's non-standard. We have computer numerically controlled machine tools, and it takes more training to be able to use those properly. And we do offer that training in a course, which is an elective in our department. You can learn how to use CNC machines. We have coordinate measuring devices to make sure that what you've machined is actually done to tolerancing according to the prints you're working towards. You can verify it was done properly. And there's an awful lot of work in terms of workstations using SolidWorks. That's a 3D CAD modeling software that is typically used on campus for our department work. Students are quite proficient at it. We train you how to use it in one of our first classes. You can go from a SolidWorks model into machine code to drive 3D printers and CNC machines. We kind of make it seamless to go from concept to CAD model to rapid prototyping. So there's a lot of good things you can use in this facility, and really as a part of our School of Engineering, we encourage our students to get involved with this. Now, the more important thing I want to take a few minutes to talk about is the curriculum, because if you become a student in our department, this is what you'll be studying for 4 years. Let me go through what the structure is and first a broad sense on this slide and some more detail on 2 more slides. The university and the Case School of Engineering, that's what CSE stands for, has some general education requirements. And these are changing over the years, so if this is what we're doing today, in 2 or 3 years it might be a little bit different story, but right now we have a structure where there's a first SAGES seminar, which is a small class, about 20 students. They're all a bit different, taught by individual instructors. And you try to learn about an interesting topic in a seminar setting where there's a lot of interaction, discussion. And then you have to learn through writing what it is you've accomplished. And it's an emphasis to practice your writing skills as engineering students. So as a first SAGES seminar, there are 2 additional SAGES university seminars, so 3 in total you'll take within your first 2 years. Chance to learn something different from your engineering course is a chance to practice your writing skills. That's very important, by the way. As a practicing engineer in the technical field, I have to admit, I probably spend more of my time writing than I spend doing calculations and running computer codes. If you don't communicate well in writing, you'll work for someone who does. And I want to emphasize that's just how the world works. Get used to writing. It's part of the profession. And it's not that bad. After practicing for many years, you get quite proficient. There are 4 breadth courses that you have to take outside of engineering, natural sciences, and mathematics. They're electives, but you have to complete 4 of them. Any department outside of engineering in any part of the university is open for a breadth course. It can be history, philosophy, economics, foreign languages. Classics is, I think, a great topic to study. It's anything but engineering, math, and science. Now, if you take those 4 classes in one department, you could actually earn a minor in a different area outside of engineering. You could have engineering major and a minor in economics. I think it's a great combination, by the way. Or a minor in a language if you want to work overseas, or a minor in history, which I think is very informative. You can choose a minor. To accomplish the minor, you need to take one additional class. Minors require 5 classes in a department, and you have the ability to do that with this structured curriculum. You have to take 2 semesters of physical education. You don't get any credit for it in terms of your transcript, but it's required to demonstrate that you're physically fit. It's just, you need to do it. If you don't do it, you don't graduate. I have to tell my seniors this story all the time. You haven't finished your phys ed requirements. If you don't finish it, you won't graduate. They're very serious about that. Now, there are some engineering core requirements that students take typically in their first year. It involves 7 preparatory classes, really first and second years, in math, chemistry, and physics. There are 4 math classes in calculus. There is 1 chemistry class. There are 2 physics classes you have to complete. That's the 7. Then there are 4 basic engineering courses taken by most or all engineering majors, and it does differ a little bit from department to department. The 4 basic engineering courses we have are a basic computer programming class you take in your first year. Then there is a chemistry materials course you also will take in your first year, followed by a course in what's called statics. That's loading of elements such as civil engineering would be involved with statics, and a bit of strength of materials is in that class. And the 4th of those classes is a course in basic circuits involving a lab, so you can learn how to analyze and build electric circuits. It's very important for all of us to understand that. There's one more departmental seminar you typically take in your senior year. It's called ENGR 398. ENGL 398 is a combination between the engineering requirements and English. And that's, again, a seminar class where you practice writing about a topic, and it prepares you for technical writing, which is a required skill when you enter the profession. Now, there are a number of major courses specific to what you plan to do in our department. I'll go through those in more detail, and it's a bit involved. So next slides look like this. Now, if you notice in the lower left-hand corner, this is the mechanical engineering program, and all that's here really are the technical classes. The breadth electives aren't here. I don't think we even have the science elective listed here, or an open elective. But this sort of tracks your progress from your first year in terms of chemistry, physics, and mathematics, calculus for the first semester and the second semester. Additional mathematics, calculus, our introductory programming course I talked about, a second physics course, and another ENGR course of chemistry materials will fill in your first year in terms of your technical or engineering courses. But there are other SAGES courses you're supposed to take which are in the open areas. I haven't listed those because they change based upon which one you want to enroll in. Second year, again, we have this course in statics and strength of materials. It's a very basic engineering course. But the first one you take in our department, which is EMAE, is EMAE 160. It's mechanical manufacturing, and we'll teach you how to do machine shop quality drawings so you can communicate the intent of a design with enough specificity a machinist can produce it accurately. In addition to that content, we have you work in the shop and have real-time in laboratory experience operating metal lathes and milling machines. You know how these things are actually manufactured in a fundamental way. And then you're certified to use those equipment also in later years. So this is a pretty important course. And you notice it's the first one, and everything else follows from that, because eventually we have to teach you how to design very complicated mechanisms and machinery, but you can't design them unless you understand how they're going to be manufactured. So we start with the manufacturing knowledge, and that's our first course, EMAE 160. Additional math in another course in our department in terms of computers or numerical methods in engineering. We start teaching that. There's a lot of work we do with computers now. I would say the most important class in our department typically happens at the second semester. It could be as early as the first semester of your second year. It's called dynamics, because this is the foundation of both mechanical and aerospace engineering. It's dynamics. Now, dynamics is a subject where you analyze with great detail, lots of calculus, the complex motions of bodies in time and space. And that's the foundation, because everything you do after that for the subsequent years builds upon that skill. And if you enjoyed the class dynamics, then you're in the right department. If you get to this point in your college career and dynamics isn't something you want to do, you may want to consider changing majors. It's that important, the decision, because that's really what we do, dynamics. I'm going to try to get my pointer to work better. There we go. All right, the circuits class I discussed, everybody takes that class. If you're an engineer, you have to understand electrical circuits, and probably in more detail than you're familiar with right now. We go through lots of detailed electrical circuits. This is the last math you'll take in the math sequence, differential equations, and then you'll start taking a class also in your second year called thermodynamics, and that's pretty foundational for our department. You learn how to convert energy from one form to another. Specifically, I take energy in the form of heat from some source, typically combustion or nuclear reactions, and turn it into useful work. That's how your car engine operates. We'll explain how that works in great detail. Your third semester, we start looking at strength materials. We use the civil engineering department for that one. They're very much experts in that area. We have a mechanical engineering laboratory where you can learn how to do experiments with great detail, which you can draw from the information to help you analyze the design characteristics and operation of components. That's a really important hands-on class. You get involved in what's called fluid dynamics, the complicated motion of fluids, the forces that are resulting from the fluid motion. Things like lift and drag on aircraft are even discussed in this class. And the last course in this first semester of the third year is called Mechanical Engineering Analysis. Now that class really is an advanced mathematics class in partial differential equations, and that's quite sophisticated. It's a requirement for all of our majors because we've discovered in later courses that you really have to master not just differential equations, but partial differential equations. And they're a bit more challenging, but it's great a foundation. So in our department, we'll take 5 mathematics classes, not just the 4 the rest of the departments offer. We go one class further. You'll finally get into what I think is the most important class in the major for mechanical engineers. That's EMA E370. That's really machine design. How do you design a complex mechanism? Complex mechanism like a car engine, for example. All things have to operate. It's quite involved. There's a lot of analysis there. And that really sets you on a good path to become a very, very strong mechanical engineer if you excel at that class. But depends upon lots of other ones before it. And all these lines are the prerequisites kind of flowing from class to class. They're color-coded by what the information is. Green is math. Purple, we look at the fluid thermal sciences. Black is the solid mechanics prerequisites. So that's an interesting way of organizing our classes. You also take a class in control engineering or control theory because everything we design today that moves and articulates and traverses time and space has to be controlled somehow. And control is an interesting subject, how one designs control systems, how one implements control systems, the characteristics of those control systems. You take a class to specialize in just that alone. We then get into things like EMA E260, Design and Manufacturing 1, followed by Design and Manufacturing 2, and that's the real details of how one goes about tackling a complicated design problem, breaking it down into some steps you can manage, all the discipline you need to have in terms of subject matter, and how to finally produce a workable, complex design. You also learn about heat transfer. It's an important subject in terms of how you design operate equipment. There's always heat generation by motion and how you can control it, abate it, use it. Your fourth year is what is, I think, the most important one in terms of your engineering studies. This course, EMA E360, is like a capstone course. Everything you see feeds into it. And the professor who currently teaches this gives you an open-ended, very complex design problem to do from scratch, involving not just solid mechanics, but fluid mechanics, heat transfer, combustion, everything. And the current project that she is using is to design a small engine that as might be used in a motorcycle from scratch. And then you produce all the drawings as if you were to manufacture it. We can't build and test them, there's not enough time. That's pretty expensive, but you learn to take a really complicated mechanical design problem and bring it all the way to the point where you can start producing it and assembling it. So that's an important culmination. There's also a senior project you tend to take in your last semester of your senior year, and that's kind of wide open. You can pick a project of your own interest. You can work on a team for a project that someone has thought of that they need some help with. The projects come from faculty. The projects can come from people outside the university who've contacted us as something they'd like to have a student work on for their business or their own personal interest at home. So there's a wide range of projects to choose from. You can work on projects alone. You can work on projects in teams. But the idea here for senior project is you've used everything you learned in your prior years into one piece of significant accomplishment that you can show to your peers, other students, and the members of the faculty, and demonstrate your competence as an engineer ready to go off in the profession. So that's an important class. It's wide open. By the time you get here, you can actually take an idea of yours and go over to ThinkBox and build it and test it and show us how it works. You can bring in demonstrations, and we really love to see those. Very, very impressive. I've seen some marvelous senior projects. Also, as you go off and try to find work, it is not a bad idea to bring at least a report for your senior project to show to a prospective employer. They're often very impressed. And I, as a former employer, once interviewed a student, wasn't from Case, but still from a good school, who showed me his senior project. And I simply stopped the interview on the spot and said, "When do you want to work? Give me a date, we'll arrange it." I was that impressed with the senior project. This can be a huge discriminator for what you're doing in terms of employment. So I'd encourage you to think about that as a culmination for your 4 years here. Focus on your senior project even when you're in your early years, like your second year. Try to get it in the direction where you think it's what you want to be able to show people how well you've been prepared for work. There are other areas here with a lot of white space. This major has 4 technical electives, which I haven't shown, which you have to take 4 additional classes. They can be in any engineering department, ours included, and so you can kind of tailor the particular major in mechanical engineering for a specialty in other disciplines. Some common ones are a series of courses from material science. That fits very well with mechanical engineering, because when we design and build something, in the end, it's wear and failure always becomes a materials problem. So if you're well trained in material science, you can do a better job as a mechanical engineer. You could look at maybe doing some courses in civil engineering if you want to get more experience in large engineering projects. They teach some classes in those areas. And mechanical and civil have a natural connection in terms of the calculation of loads and their distribution. Only difference is the civil engineering problems are stationary, our problems are moving. But the same fundamental courses apply to each. You could tailor it any other way you want. You can sometimes even take additional mathematics classes. We'll count those as technical electives. So you can make a big impact to the higher level courses you take, and there are 4 of them. There's also an open elective, which means you could, if you want to, take those 4 tech electives in one department, use the open elective for one more course, and you get an engineering minor in a different department. So you can major in electrical, you can major in mechanical engineering, you can minor in electrical engineering. We give you the flexibility in your schedule to do that if it's of interest. Or a major in mechanical and a minor in materials. So there are ways of doing majors and minors with this particular mechanical engineering program, and it's up to you. If you're interested, your advisor can help you plan your courses, but you can do one major in mechanical engineering. You could get a minor in a field outside of engineering, and you could pick a minor in a different engineering discipline together. So you get one major, 2 minors are possible. All right, let me talk about aerospace next. This is a bit more complicated. And if you notice, there are more boxes on the screen because the aerospace major requires more required courses. Pretty much everything through the second year is very common with the mechanical engineering program. The courses are about the same. We require you take an additional physics class because aerospace engineering has some more advanced subjects that can benefit from a modern physics course. But the rest of these classes are pretty much identical. Now, you get into some differences in your third year where you have to take classes in EMA 359, aero gas dynamics, that's high speed compressible flow, and aerodynamics, how bodies produce lift. So that's a specialty for aerospace engineering. In your 4th year, you learn a class called orbital dynamics, how spacecraft move between planets in the solar system. A class called flight mechanics, how aircraft move through the air, their flight characteristics, how they respond to control surfaces. So those are 2 new courses. What else do we have you take? You have to take a class in propulsion in your senior year. That's different from what we require for the mechanical engineers. And the culmination for the aerospace engineering program is something called aerospace design. You take it in your last semester, all the classes kind of feed together into it. And I actually teach that class. And this semester, I break the class up into 4 teams. I have 2 teams working on the same project kind of as in competition. And one project for 2 teams, they're working to design a crewed mission to Ceres, which is the largest asteroid in the asteroid belt. It's actually a minor planet. And it's of interest. There have been some probes sent out there recently, and Ceres has some interesting characteristics. So NASA is actually looking at plans for doing a Ceres mission in the 2040 timeframe. And so their students are trying to design an entire interplanetary vehicle from scratch, all propulsion, structure, life support systems, science, the whole thing. Very, very complicated design project. We've done missions to Mars, missions to Venus. We do different missions each year, but you have to design something very complicated that goes off into space. That's one half of the class. The other half of the class does a design for an airplane system. And this current year, we're doing 2 teams designing a personal jet aircraft where it has 1 pilot, 1 passenger. It can fly 1,000 nautical miles. It's kind of built for fun. It has some maneuverability characteristics which are required. You have to design the whole thing from scratch. There's the structure, the shape of the aircraft, size of the wings, determine how fast it flies, how high it flies, how far it flies, design the propulsion system, the engines. And in principle, this project is intended to be able to show that you can actually design a small jet aircraft that can be probably purchased by someone of a relatively, middle or upper middle class income bracket, which would be able to cost about $150,000, and that's attainable. I sail boats, and I buy sailboats about that price range, and you can afford it later in life. So why not have a jet aircraft you could buy too? Which is the intention for that one. So there's a lot of economic considerations for the designs also. Now, for these courses in this major, there are only 1 technical elective available and 1 open elective. So it's kind of hard to tailor the aerospace major in any particular way because there are only relatively few courses you can use as electives. What many students choose to do is to overlap both majors, mechanical and aerospace, which means I have to bring in 3 required courses for mechanical to fill in my electives, and I have 2 I can use in the schedule, and 1 more course will finish the 3 from mechanical. So you can get the double major in 4 years. You have to tuck in 1 extra course that you wouldn't have taken if you majored in just one or the other. And for 1 extra class in 4 years, that's a pretty minimal payment to have 2 majors. I do want to make a point that as a former hiring manager for 25 years in industry, if a student were to walk in my office and present themselves as a employee who could do either mechanical or aerospace because they have both majors, I'd be very interested in hiring that person. That's a unique combination. That's not very common. Most students have just one or the other. In our department, you can get both, and that opens up your employment opportunities substantially. And if you are interested in aerospace as a profession, I do have to caution you that do the really fun stuff you see, all the fancy aircraft and spacecraft, that tends to require a bit more education. Most people I know in the profession have picked up at least a master's degree, and most of the really fun, cool stuff is done by PhDs. So if you want to start in aerospace engineering, you'll often start a job which is more focused on the mechanics of the components of aerospace systems. Having a mechanical engineering degree along with it just makes you even that much more attractive as an employee starting out. It's a great way to build a career. Your first few jobs when you start in aerospace will probably be more focused on mechanical engineering, but eventually you can get more skill and knowledge and perhaps another degree and advance your professional interest where you want them to be in 10 or 15 years. All right, that's the curriculum. I know it's a lot. These particular slides are available on our website, and if someone asks a question later today, I'll show you where to find it quickly. Let's move on and talk about some other stuff. Now, undergraduates often can get involved in research with the faculty. Not all students do that. Some are interested, some aren't. But here are some of the current areas where there's research and undergraduates do participate. One of the biggest areas is robotics. We've got quite a few members of the faculty doing research in robotics, legged robots, soft robots, nervous systems, because these robots are biologically inspired. We try to make mechanical analogies to things like cockroaches, because they're relatively simple mechanically with 6 legs, and they have a very simple nervous system, and we try to make them a model of a biological organism and see how it works. We look at different neural networks in software as opposed to tissue. We do a lot of collaboration with people in the Department of Biology. We have some work being done in terms of soft robots that articulate like snakes or worms and how they can maneuver and how you can control that. It's very, very complicated. A lot of opportunity for undergraduates to work in these laboratories because once you've learned how to make things, you've gone through our first course, you understand how to work with machine tools, milling machines and lathes in particular, you can go to the laboratory with this group and start helping them build parts of their robots because everything is done from scratch. And you can be a strong contributor. You can learn more from the graduate students who you're working side by side with, and they may help you focus where you want your career to go eventually. So that's a great way to get involved. You've learned how to make things. You can be useful in the laboratory making special equipment or mechanical devices for the researchers. We've got a large group in terms of work being done in biomechanics, which tends to be things like joint implants, how tissue grows with a solid surface, and hip implants, knee implants. We're looking at growing artificial organs from scratch, being able to deposit cells of certain types into tissue so they can grow and become replacement organisms. That's pretty cutting edge. Doing a lot of work with blood assays, trying to understand the fluid mechanics, the chemistry, the biomechanics of blood. That's very, very complicated. A lot of diseases are carried through the body through blood. So these people are working with soft tissues, bones. It's still really mechanical engineering, but it's not things like steel or plastics. And they're always doing research on the characteristics of bones and soft tissue, how joints work, the wear characteristics, how the loads are transferred from one member to the next. A very active group. You can get involved in their research too. There is some work being done in terms of what we call aerospace. A lot of this is being done in conjunction with NASA Glenn, which is a research center here in Cleveland, Ohio. It's about a 20-minute drive from campus. They have some great facilities our students work with. We're looking at flame spread, how flames spread across materials in microgravity. And in NASA Glenn, there's a drop tower. It's 500 feet deep. They draw a hard vacuum. They drop a payload so it can go through 5 seconds of microgravity before it impacts the bottom. You could do a test in 0G, and you can get really interesting results in terms of the characteristics of flame spread where there's no gravity, because it behaves very differently than the flames you see at 1G that you're used to. And flame spread in aerospace systems that have people in spacecraft, really important topic. You got to find somebody to control it, and it behaves very differently than it does on the ground. That's a very active interest area of research right now. We do have some research being done in terms of the general topic of energy, and there is something called the Great Lakes Energy Institute, which brings in research projects that people from different departments can collaborate on. Things like renewable energies, photovoltaics, solar power, wind energy, wind turbines, how they can capture energy, how they can store the energy, how they can then use it. A lot of growth area for this kind of technology in the future. There is some basic mechanics research being done. The effect of impacts on material properties, and impacts, we really mean impacts at very high velocities under extreme loading conditions, where things move at not in meters per second, but in kilometers per second. The kind of impacts you might experience if you have things bumping around in space. Material behaves very differently under high velocity impacts than low velocity impacts, like a car in an accident. It crumples. If a solid object impacts with a solid object going at 7 kilometers an hour, it doesn't crumple. It changes phase. It does amazingly different things. The metal behaves like a fluid suddenly before it becomes a gas. Very interesting properties of mechanics under high loading conditions. We've got a number of faculty doing basic research in fluid and thermal sciences, and that was actually where I got my PhD in that area. Right now there's firefighting, safety, detonation kinematics. There's all kinds of basic research in high-speed fluid mechanics for supersonic flows, hypersonic flows. A lot of important research being done in high-temperature combustions for different kinds of engine designs. And a lot of this work is also being done in conjunction with people at NASA Glenn. And I did my research for my master's thesis and my PhD out at NASA Glenn. They have phenomenal facilities, as I earned my degrees here at Case, because the two places are only a 20-minute drive apart. A lot of opportunities between Case and NASA. Now, these lists will change over time. They're not static. Research changes as there are different interests and funding available. So this is today's list. In 2 or 3 years, the list will be different. And as a student, you can expect to see changes. And they make opportunities when new ones arise. With new research, faculty look quickly and hard and almost scramble for graduate students. They can also use talented undergraduates to help them start the research projects when they have suddenly gotten an award. And these people here have gotten a lot of large research grants in the last 6 months, and they're looking for people day and night. They can't find enough fast enough. They got too much work that they've suddenly managed to win, which is a good thing. Now, in terms of what you can look at besides courses in our department, I would encourage you to think about student design teams. We have a number of them I'll talk about briefly, and this is stuff you do outside your courses, but it's a great way to learn about what it means to be a good engineer. This team is called Crewbotics, and it's really a robotics team which does competitions nationally. It was founded in 2012. There are about 50 active members, and it really draws from mechanical, electrical, computer science. It's kind of interdepartmental. So you can work with people across different departments, different skills, different experiences. They do NASA competitions. The NASA robotics mining competition has been done. They do national robotics challenges. And when they go compete in different places, this is a competition which is done at the Kennedy Space Flight Center. And a lot of this is done sponsored under NASA. It gives you a chance to get out of the campus to some other state and compete with students from other universities and see how you stack up. And I'm proud to say you stack up pretty well. Over the last couple of years, this team placed third overall in 2018, placed first in the systems engineering paper in 2017, placed second in design presentation in 2017. And I really haven't kept the slides up for the last couple of years, so they're equally successful results in the competitions. And you get to go fun places. The students one year got to see a tour of Kennedy Space Flight Center, and that is a Saturn V rocket lit inside. You can walk under it. It's an amazing thing to see how large it is, how complex it is. Those are the real engines attached to it. And it's quite a visitor center, and you get a chance to see that and other things when you do this kind of competition in national, within national competitions. If you are just what I would consider a traditional mechanical engineering student, the team to join is called Baja SAE. And it is sponsored by the Society of Automotive Engineers, and you have to build from scratch and then compete an off-road vehicle under a pretty tough track. So there are about 25 active members. They've done pretty well over the years. But this is what it looks like. There's really a single seat car. You have to design the suspension, you buy the wheels, you have to design the entire frame, steering system, you have to design the transmission, you have to use a standard Briggs & Stratton 10 horsepower engine, so it's the common engine across all the competitors, but everything else is your design. And it's kind of fun to watch the students in the spring because they actually test drive this thing in a field just outside my office. I can sometimes hear and watch them doing it, and it's pretty messy. They get an awful lot of mud. They build little obstacles to test themselves on. One of the big challenges is when you design this thing, you go compete it and it breaks. They all suffer failures. And the question is how fast you repair it and get it back running. It's a real car race. Professor Bachman, the fellow here, is very involved in this team, and they're quite active. If you like making machinery like cars, join this team. You'll learn an awful lot about it. The students I've found who join the team are really good students. They know a lot, beyond what we teach them in classes, by the way. More examples of what these things look like, what you have to do in the competition schedule, and that's a picture really of someone testing in the field outside my office, and it just gets muddy. But they seem to enjoy doing it. And by the way, it's usually in March, and it's pretty cold mud. That's not very warm, but they really want to make this thing work. They test it thoroughly. Fun to watch. All right, other teams, there's the Case Rocket team. This is an interesting group of people who are very, very motivated to launch large rockets as high as they can, tens of thousands of feet in the air. You have to get FAA approval to do those launches, by the way. It takes years of practice and rigorous certification to be able to do these launches, be in control of them, because they're quite dangerous. We don't cast the motors, you have to purchase them, but they're large, essentially munitions at that size, and they're very dangerous. You have to be very careful how we store them. But the flights are thoroughly and interesting and enjoyable, and these rockets all have real-time telemetry, sending information down during the flight, and their objectives to achieve in different competitions based upon the design of your rocket, its payload, and its launch objectives. And it's pretty advanced engineering. A lot of electrical engineering, communications, radio telemetry is very important. Interesting stuff. Very motivated team. I'm the academic advisor for this team, and I worry about them because they're doing dangerous things. And I just don't want them to show up on the nightly news with a bad accident. So they've been pretty safe so far, but if I had to think about what team I spend most of my time concerned with, it's this bunch. But they're very, very good students. They're very, very competent, and they work with people who are professionals in terms of these national launches, and no one's gotten hurt. The other team I'm the academic advisor for is the Case Aeronautics team, and this is a competition that is sponsored by AIAA. It's called Design, Build, Fly. Every year, Raytheon Corporation puts forth a very, very complex aircraft competition involving the flight conditions, essentially a flight path, and these aircraft do different things. They have to deploy things, drop things, change their configuration. This is difficult work, and they have to build the entire aircraft from scratch. The only thing that is common is the electrical motor is a certain motor. They have some different types of propellers they can use, and the electrical batteries to fly these things, there's limited ranges which you can use. But these are all electrically powered vehicles now. In years past, used gas engines, but now everything is electrically powered. This is a pretty enthusiastic team also, and I really appreciate the work they've done. They have to build the entire thing once it's been designed out of some lightweight material. Often it's balsa wood or spruce. They use the laser cutters to make the parts. It's fast and it's accurate, so that's kind of evolved. Laser cutters shown behind these guys here, and they have to design this whole thing from scratch. And here's an example. For this year, they had to carry a certain size payload, a block of wood of a certain mass, someplace within the cockpit of the aircraft. They had to deploy wiffle balls at certain points of the flight trajectory precisely at the right time, at the right altitude, which is hard to do when you're trying to build this from scratch. So doing this kind of aircraft work involves lots of intricate mechanisms. So being a mechanical engineer is really a great match for the aerospace engineering program. And then they have to go test it and fly it. And they have to fly it sometime in basically March, which is cold in Cleveland. Also, it's pretty windy. So those flight tests are tough to do sometimes. They're hard to control because this is the first time they've flown it. Sometimes it doesn't fly the way they expected it to. But they're a good bunch. Now, here's a few students that I know because they're my classes. They took 4 undergraduate classes with me, and 2 of them took 2 graduate courses. So I got to know them very, very well. They're actually at the Wright-Patterson Air Force Museum, which is about a 2.5-hour drive from Cleveland. And you can go see virtually any aircraft built by the nation. If you look behind this fellow's shoulder, there's an SR-71, one of 5 you can see in the country. It's not a long drive from Ohio. I always encourage this team to go see the stuff at Wright-Patterson Air Force Base. The planes are amazing. There are 4 different hangars you can walk through. Quite a sight. I was there many years ago. As you become a senior, and these are senior students shown here, you understand why this aircraft looks a certain way, why that aircraft looks a certain way. The objectives of what you want the aircraft to do dictate how the design has to end up in terms of its geometry and its features so it can meet the flight mission. Now, these students were, again, very good students. The first one here on the left is Tobias Behrens. This is Amma Carney. This is Sarah Ryan. And this last fellow here is Alex Yaney. And it was such a pleasure to watch them go from my classes in one semester to the next and then stay on. The 2 here, Amma and Alex, went to do our graduate program. They did the BS-MS integrated graduate program. And year after year, I watched them get better and better. And it was such a pleasure. And I want to talk about Amma briefly. She was a very interesting student because she was so enthusiastic. And as she became a grad student in my courses, she'd often, engage me in discussion about her future career objectives. And she said she wanted to do work in basically, thermal control systems. She really enjoyed that. And I taught her advanced thermodynamics, so maybe that helped her make that decision. And she had some questions where to look for employment. She wasn't sure where to go. And so with more and more discussion, I finally mentioned, well, there's a company I consult with who really does look for people like you. Maybe we can make an arrangement. And she said, it'd be really great if I could actually stay on and then get my PhD on a part-time basis and have the company pay for it, which is how I got mine, by the way. So I helped her arrange getting hired last summer with a company I know very, very well, all the founders and the senior engineers, and she's now working there, and she's coming back now as my PhD student on a part-time basis. So what she wanted to do, we were able to help her accomplish, and that sometimes happens, but it's all on an individual basis. And the fact that Amma asked me repeatedly what she should do, I started thinking about how to help her, and her future looks brilliant. She's really talented. Her job is going phenomenally well. Her boss couldn't be happier. I've got one more very, very bright student who we're going to have work on a research project in collaboration with NASA. I like it when things work out that way. So I've known her for about almost 3 years now. I hope to know her for another 5. One great success story, and there are many other ones. All right, there are some other competitions you get involved with. I'll skip these really quickly. We sometimes do autonomous lawnmower competitions where they have computer systems to detect things and avoid them. Same thing with autonomous snow plows. This is kind of fun. We get a lot of snow in Cleveland, Ohio occasionally. You can do other kinds of teams which involve Design for America. That's a much bigger design effort. It's sponsored from Northwestern University. You can get involved in design activities that involve human beings, the impact of society. This is in conjunction with the Cleveland Institute of Art even. So you can go beyond engineering if you're interested in this, and they look to use our students all the time. But their focus is beyond just engineering. It involves improving society. And last but not least, sometimes companies come to our department and ask us to do a competition. This one was a few years ago. Parker Hannifin is an aerospace manufacturer of components. They wanted our students to compete in retrofitting a bicycle to be able to drive without using a sprocket and chain, but pedals driving a hydraulic pump and a hydraulic motor. And they did a great job. And they would run this thing through the hallway outside my office and make sure it worked. And that's kind of unique. So this happens on occasion. I have no idea what's going to happen in the future, but there'll be something interesting you get involved with nonetheless. All right, that finishes my presentation. So I'm going to stop my share. And if anyone would like to ask some questions, I've got a few minutes I can answer them.
Yeah, so I know that you talked about the possibility of getting a minor. This student was specifically interested in the possibility of doing a double major in something outside of engineering. Maybe, how do you see that fits in with the curriculum, and, how possible that might be.
Sure. I'll give you an example. Every year I have a student, sometimes two, who major in mechanical or aerospace engineering and minor in music. I can't think of a more diverse set of objectives. There's almost zero overlap between music and engineering, and yet they are able to do it. But if you want to do a double major, a full major between engineering and something far removed like music, it'll take you at least an additional year to cover all the requirements for each of the majors. Now, all the students I've known who've done that, mechanical engineering or even the dual major, mechanical aerospace and a major in music, for example, have gotten done in 5 years. And one of the ones I was most impressed with, who graduated about 2 years ago, decided to pursue his love of music and try to join an orchestra as a trombonist. And I couldn't convince him to stay in engineering because he really wanted to see if he had a challenge, if he had the talent to succeed in music, and that's where he wanted to start. But he was able to do both. It just took him 5 years as opposed to 4. So if you want to be doing a double major outside of our department, it could be even a double major in engineering or one outside of engineering, you'd have to think about a 5th year to accomplish that because there's more classes you got to take. It's well beyond just 5 classes. It might be 30 credit hours. It could be about another year worth of studies to do both.
Yeah, and along those same lines, a student was asking about summer courses as part of the 4 years. There are summer courses available for students, and I know many of our students take advantage of that. Go ahead.
Yeah, we do have summer classes. Often they're offered because students are struggling in one semester and want to try to make it up in the summer. I try to encourage students to go off and enjoy their summers, honestly, because at some point in life soon, you'll never get a summer off ever again.
Yeah,
that's just how it works. And when you're a student, you can do interesting things in summer, like an internship or do something you really want to do while you're still young. But if you really want to keep on taking classes over the summer, you can, but there are relatively few compared to the requirements. So I have seen students take their breath electives over the summer just to speed things up. But I would still recommend you think about enjoying your summers while you still have the chance. Because once you start working, forget about it. You don't get summer break ever again. And I can't remember the last time I took a vacation personally. I'm just always so busy. It's not going to change anytime soon.
So you did talk about the teaching students with ThinkBox, but this particular student was asking about if there are specific assignments that are outside of that initial class that you're teaching students where they are mandated to use ThinkBox.
No, they're not mandated, but they have it available if they wish to use it. So some classes, especially your senior project, that's a wide open, you pick a kind of class. You can go spend all your time in ThinkBox making the thing you want to design and demonstrate it can work. Often our students do senior projects in the area of research with faculty and have to build an experiment. Well, you go build over ThinkBox. You take it back to the lab and you see if you can make it work. You take some data and you prove a theory. That's a really great senior project, by the way. So our students are very engaged in the senior project, but it's not required for the other courses we tend to teach because, quite frankly, most of the courses you take are basically lecture, homework, exam kind of classes because you have to learn the theory and the mathematics. And there are a few classes where you get involved in building things and prototyping, and ThinkBox is there for your use. But we don't mandate you have to do it for this class versus that class. We try to stay flexible.
Yeah, so there's a couple questions here about the co-op experiences. One of the students is asking, if the students get resource and support to find and secure the co-ops. Another student was kind of asking specifically about the percentage that you included, whether that was students doing one co-op, or do do typically students do the dual, the full year co-op, or the one? So maybe you can piece out the co-op a little bit.
Sure, I'll take it in reverse order. Most students do a 2-semester co-op, but that's not semester back-to-back. It's semester 1 year, semester another year. That's the common form for co-op. A few students only do 1 semester co-op. It just seems to work out for them. They've had enough. They don't want to do it a second time. They've learned what they wanted to know. In terms of support for co-ops, there's an office that helps you establish connections with companies. That's the co-op office. You can just walk in there and ask them, can I see a list of companies who are looking for co-ops? They help you put together your resume. They help you get a connection with the company. The companies essentially hire you. There's an interview process. And the office is there to help match you up with your interests with companies who are looking for co-op students. And that'll be a great asset to you. They also have some offers for summer internships that you can take advantage of, but most students I know are able to arrange their own summer internships without going through the co-op office, because that's really just summer work when you think about it. But if you want to do a traditional co-op, there's an office to help you do that, and they're a great support. And Janine Apodini is the one running it, and she's great to work with.
And I should say, from my experience too, professors like Dr. Barnhart are fantastic resources for our students. They are just like the story that you gave before, making these connections and having these ideas and helping students through the process of kind of what they want to do is really a wonderful resource for students. There are some questions here about dual enrollment courses. I'll quickly touch dual enrollment. We do have a website, and I can put that in the chat for you, but essentially there are some rules about what classes might transfer. The main thing about dual enrollment is it can't be double counted. So if it's being counted for high school graduation requirement, it can't also count for your bachelor's degree at Case Western Reserve. So that's the main factor. But Dr. Barnhart, can you speak to maybe advising students if they were to get a credit that would transfer, do you have any recommendations for students about those kind of credits, whether they should take the class or not, how that works?
Well, my advice is if you're going to learn something, take the class. If it can transfer and get you something later on, that's great, but take the class and learn always. You could try to reach out to members of the faculty if they can give you more specific feedback in terms of class specifically. We might be able to help you. I often get involved with students who transfer in or looking at what will transfer from the university in terms of credits, how AP credits work. That's constantly being done. The faculty are all proficient. We can give you some advice. Just reach out to us. But the university will give you credit for courses when they can. They can advance your studies by saving you the time to take the class here if you've got the credit from someplace else. And you can use that schedule to take something totally different that you're interested in. You can fit in within your 4 years. It gives you some flexibility. Or you can try to get done a little earlier, but sometimes that's not worth the effort to try to get done a semester earlier. And there are reasons. We don't always teach every class each semester, by the way. But you'll learn about those details eventually.
So there's a number of questions here about the senior design. And one of the students asking about if you can talk a little bit more. It sounds like the student initiated projects versus industry led. Just kind of talking about the senior design. And then another student that was asking about the design work as well was how, or if you had an example or how it might work with the students who are doing the double aerospace and mechanical.
I'll take the last question first. We only have one senior project. It counts for both majors. You can do your senior project in any area you please. It can be focused on mechanical or aerospace. We don't draw a distinction as long as it's your project and you've done some challenging work. In terms of what project you want to do, I would encourage you to think about ones on your own if it's interesting. You have a chance to do it. Often students find projects with the faculty members they know from their classes because they have a research interest that could use their help in the lab. It can become a senior project. We sometimes have industry that comes by and says, could we get some help with this particular design we're trying to do? And those are interesting, but they're so wide open. I really can't give you a criteria as terms of what works. As faculty, we try to be very flexible for your interest and outside people's interest to get challenging design work done in your last semester before you go off and do it the rest of your life. It's up to you. And I've taught that class before, and I try to be really broad-based flexible in terms of senior projects. Not everybody designs something, not everybody builds something, not everybody tests something, but you can if you want. I've had some students do senior projects in purely analytical research because they really wanted to do that. And it was a contribution, and it was their project. They can be quite diverse. It's up to you. And I think that flexibility is beneficial.
Thank you. I think that's such a wonderful point about that flexibility and working with our professors and students. This is a great question from a student about working on projects related to the medical field, if you're a mechanical student. And have you had students who've also taken the pre-med path in your classes?
I'm not sure about the pre-med path because no one tells me unless they look at their declared majors and minors, which I tend not to do. But yeah, there have been students who have gone through our department, done the pre-med route and the rest of it. I have an artificial hip. Got a replacement some 5 years ago. I was pretty young when I got done. There was an injury involved. The surgeon was a mechanical engineering major in our department. Went on to do biomedical research, got his MD degree, and was a great orthopedic surgeon. I'm thankful for my implant. So that's a great connection between biomechanics, mechanical engineering, and eventually medicine. You can do it. It just takes a lot of years of your time because the medical degree is a lot of work beyond engineering. And I think it's wonderful if you can do it. If it's your interest, we'll try to facilitate it. But the requirements for engineering don't necessarily map really well with the pre-med requirements. So you have to anticipate taking additional classes to do engineering plus a pre-med and then go to med school. It's an investment. It's an investment for your entire life. And I want to stress that it's a really large investment, time, money, and it specifies the rest of your working career. It's a long path. By all means, if you want to do it, go right ahead. We'll help you get there if we can.
Yeah, so one of the students is asking about studying abroad or doing research abroad. Obviously, in a pre or post-COVID, when we can kind of have those more open borders, what have you seen, Dr. Barnhart, with the students in this in your field?
I get questions about study abroad all the time. And this is what I tell all the students. If you want to study abroad, it's risky to try to find an engineering course that will transfer back to case. It's not impossible, but it's often difficult. So I simply tell them, plan on taking your breadth electives on your semester abroad, because those are anything you want. And one university's non-engineering courses in history or economics will transfer just fine. So those are great courses to study abroad. It's difficult to find an engineering course that matches ours because if you identify one of the university overseas, you have to get the professor's approval in writing here at Case, and often they're pretty particular about if it's the same class they're teaching versus what's being done overseas. And I've had to turn down quite a few students over here saying, no, that's not the same class I teach. You can't get credit for that. So you can always get credit for a non-technical course of study overseas. Sometimes some of the more basic engineering courses map over pretty well, but by the time you get to your junior and senior level classes, they're pretty specific and they're pretty hard to map over. They often aren't the same classes. So I try to think about the breadth electives in terms of what can transfer easily. That always seems to work.
So this is a question. I think we have maybe two more that I can ask, but this one's asking specifically about following graduation and grad school. It seems like, are students going into grad school mostly, or are they going into industry? If you can touch a little bit on what students tend to do when they leave the university.
Most of them, by far the majority, go to work in industry. And that's as I would expect, because you're really well trained to get a very challenging job that pays awfully well. It's a great career path. And most students are encouraged, just start working. You'll find your way through it. It'll all work out great. Work. Occasionally, some students really want to learn more about the topic and they want to continue on in grad school. I'd say most of the ones I write recommendation letters for go to different universities for their graduate degrees. Some stay on at Case either through the integrated BS-MS program, or they just want to stay on at Case like the professors. That's kind of common. And I have a number of students that have come back after they started working who are still in the local area and take classes part-time to pick up a master's degree. And as I said, I got one right now who's working on going to continue for her PhD while working full-time. I have two other students working on their PhDs while working full-time. So it just depends upon your interests. If you want to get more education, I would recommend a master's degree. Think about it. You'll learn a lot more. It'll be very, very useful. Think about a PhD a little more carefully. It takes a lot more of your life. It tends to be very specialized. It may take you a different direction you think right now. It tends to be focused really on research or going into academia. But people do get their PhDs and are very successful in the industry. I was one example. So I'd say relatively few go the graduate route right away. I've been working with lots of students over the years who come back and say, I want to start a graduate program working for 4 or 5 years. Where can I go? And they find all kinds of schools. There's lots of opportunities. Don't have to get a graduate degree, but you can. If you want to do it, I recommend it. It's very beneficial.
So last question, and thank you so much for your time, Dr. Barnhart. What is the best thing about the department that it has to offer? A lot of the students who are here listening are in the place that they're trying to decide what institution to make their home in college. So what does our department, specifically, have to offer these students?
All right, I'll speak on a personal level. I was a student here once as an undergraduate. What I discovered, and I didn't start at Case. I went to Cornell first when I left high school. Much bigger school, really good engineering department. I was a mechanical engineering major. And then I transferred here after working for a couple of years. I wanted to learn a trade when I was younger. But I discovered this was a really good engineering department, outstandingly talented professors, and it was small. It was not large. I got to know all my professors personally, and some were lifelong friends eventually. They knew all the students. I teach classes of maybe 30 students. Our largest class we'll teach in our department is maybe around 100. And then we'll start thinking about offering up both semesters to get the numbers down. When you're in a class of, say, 30, 50, even 60 students, there's lots of good interaction. You get to know your professors, the professors get to know the students. That's priceless. When I was a student, the professors knew me, knew the work I was doing for my senior project, was doing research on the professor. I had an opportunity to go to grad school because of that. I knew the professors for years after the fact. They were the first introduction to the profession because they knew me, I knew them, they helped me get jobs. I can't say enough about the faculty. That's really important in a school our size. If you go to a large land-grant institution like Penn State or all the big state schools, you'll be in a class of maybe 500 students. It's very hard to get any kind of personal connection that way. I look at that as invaluable. Personally, it made a huge impact in my life. It's one of the reasons I came back to teach, because I knew the faculty for so many years. They knew me. It was an easy connection to make, and it was a good decision. If I hadn't had that, I don't know if I'd be here talking to you today. I'd be doing something else. So that's my argument for Case is a great place to go. Top-notch education, lots of opportunities, and you get to know your professors very, very well.
Well, thank you so much. I mean, I think that's a wonderful place to end this session. I appreciate your time. If students do have more questions, I will throw into the chat a way for them to contact us. I also earlier put in the chat the website, which you included before, Dr. Barnhart. So thank you, Dr. Barnhart, for your time. It really reiterates our faculty are here, they're engaged, they're really interested in the welfare and supporting our students in the future. So appreciate your time.